In this video, we will return to our exponential growth model, but with a new twist. Let's revisit our example where we have a bacteria colony growing on a petri dish. Using an exponential function, we found a good model for this population to be P of t equals 160 times 1.5 to the t, where t is the number of days that the bacteria colony has been growing, and P of t is the population after t days. Remember, in this model, our original population was 160, and we grew at a rate where each day we had 1.5 times as many bacteria as the day before. Is this really a good model? Previously, when we looked at this model, we only looked a few days out. But what if we ran the experiment for 100 days? Then the population of the bacteria colony after 100 days, P of 100, would be 160 times 1.5 to the 100, which comes to roughly 65 quintillion. That is 65 followed by 18 zeros. This is unreasonably huge. And it gets even worse if we looked after a whole year. Why is this so bad? Because there's only so much space on the petri dish to grow. There's no way that a colony that large would fit. The model we had before is only good for smaller values of p, because in real life it can't grow infinitely big like this model can. So we need a new model that won't grow so big. These are some of the traits that we want our new model to have. We still want it to behave like an exponential function for low populations of p. But we need a maximum value for P of t so it won't grow infinitely big. We call this maximum value the carrying capacity and denote it by L. The function that we will use that has these traits is P of t equals L divided by 1 plus c times e to the negative kt. Let's look at why we use this function. As time goes off to infinity, the exponential function e to the negative kt in the denominator goes to 0. So the function approaches L over 1 plus 0, which is just L. This is the maximum value that we wanted. And for small values of p, this function behaves like the exponential function p naught times e to the kt. So it behaves like an exponential function for small values of p as we wanted. Let's now visualize this function by looking at its graph. So we will plot time t against the population p. In our graph, we want to include when p equals our maximum value L, because we know we don't want our population to go above this line. Now, as we draw our graph for p, we want it to start out like an exponential function, but we know it can't grow like this forever. So eventually we reach a point where the growth has to slow down. And after this point, our function can't grow infinitely big because it has to stay below the line p equals L. So as time goes on, our population gets very close to our carrying capacity L, but it never goes above it. The point where we see this change is called the point of diminishing return. Notice that at this point, our function changes from concave up to concave down. So the point of diminishing return is the inflection point of P of t. Since the point of diminishing return is the inflection point, we know that the point of diminishing return is an inflection point, we can see that it's the place where our function P of t increases the fastest. While this is a great model for populations, it can also be used to model the sale of an item. In the application where P of t is modeling sales, the point of diminishing return is when sales start to slow down. Let's take a moment and see why P of t is a good model for sales. Consider an example where we are selling a record for a new band. In the beginning, not a lot of people have bought the album, but as some people buy it, they tell their friends, and they tell their friends, and more people are buying it. So our sales are going faster and faster. But eventually, our sale rate peaks, and our sales start to slow down. This is at the point of diminishing return. Then, our sales get slower and slower, and eventually we reach the point that the market is so saturated that everyone who planned to buy our product has already bought it. This is our carrying capacity, L. So our conclusion is that this is a good sales model for products that consumers would buy only once, like movies, records, and so on. But it wouldn't be a very good sales model for perishables like food. At this point, we have seen that the point of diminishing return gives us a good understanding of what's happening with our function. So what is the point of diminishing return? How do we find it? Recall that we saw the point of diminishing return is the inflection point for P of t. So we need to find when the second derivative of P equals 0. This is a long calculation that we will put in another video. In the calculation, we will find that the point of diminishing return happens when P equals L over 2. That is, growth slows down once P is half of the carrying capacity. It's important to note that this gives us the value of P, not the time t. Now let's look at an example. Suppose that we can model the sales of calendars as P of t equals 2000 divided by 1 plus 99e to the negative 0.6t, where t is the number of days since December 15th. Can we find how many calendars were sold by December 24th? In our question, the phrase, how many calendars were sold, is asking, what is P? And the phrase, by December 24th, means for T equals 9, since December 24th is 9 days after December 15th. So in other words, this question is asking, what is P of 9? Using our model, we can compute P of 9 as 2000 divided by 1 plus 99e to the negative 0.6 times 9, which comes to roughly 1382. So according to this model, approximately 1,382 calendars will be sold by December 24th. Can we also use this model to find the most number of calendars that we will sell? The most that we will sell is the highest value that P will reach. This is given by the carrying capacity, which is 2,000. So the most number of calendars that we will sell is 2,000. We can also ask, on which day will the calendars be selling the fastest? To answer this, we first must understand the question. The phrase, on which day, is asking, what is T? And we know that when we are selling the fastest, we are at the point of diminishing return. So our question is, what is T at the point of diminishing return? Recall, we found that at the point of diminishing return, our function p equals L over 2, where L here is 2,000, our carrying capacity. So the point of diminishing return is when p is 1,000. But that doesn't tell us which day this happens. It only tells us that we will be selling them the fastest once we have sold 1,000 calendars. So the question that remains is, what is t when p equals 1,000? On the one hand, we want p to equal 1,000. On the other hand, using our model, p equals 2,000 over 1 plus 99e to the negative 0.6t. So we need to solve the equation 1,000 equals 2,000 over 1 plus 99e to the negative 0.6t. Notice that we have turned our word problem into a strictly algebraic problem. To start, we'll multiply both sides by the denominator. On the right, leaving only 2,000, and on the left, we'll have 1,000 times 1 plus 99e to the negative 0.6t. Now dividing by 1,000, we get on the left 1 plus 99e to the negative 0.6t, and on the right 2,000 divided by 1,000, which is simply 2. Working further to solve for t, we will subtract 1 from both sides to get 99e to the negative 0.6t equals 1, so e to the negative 0.6t equals 1 over 99. Now to get at t, we need to use the inverse of the exponential function. This is our natural logarithm. Taking the natural log of both sides, on the left we have the ln of e to the negative 0.6t, and on the right we have the ln of 1 over 99. But the natural log of e to the negative 0.6t is simply negative 0.6t. Now all that's left to solve for t is to divide by negative 0.6. So we get that t equals the natural log of 1 over 99 divided by negative 0.6, which we can calculate to roughly be 7.66. So going back to our model, we have that p equals 1,000 when t equals 7.66. Because this is the number of days since December 15th, that means that we will be selling calendars the fastest on December 22nd. Let's now look at one more example where we try to build our own model. In this example, suppose that the downloads of a new album can be modeled by the Logistic growth model. Suppose that to get the music out, we distribute 2,000 downloads for free. We notice that in the beginning, sales are growing exponentially with a continuous growth rate of k equals 0.1. But then, sales start to slow down once we have sold 200,000 copies. What is the Logistic growth model for the sale of downloads? To find our model, we need to figure out what L, C, and K are. One of these we are given right in the example, that k equals 0.1. But what about L and C? To find L, we will use that sales start to slow down once we have sold 200,000 copies, which means that the point of diminishing return happens at p equals 200,000. But we know the point of diminishing return happens at L over 2, which means that our carrying capacity L must be 400,000. Finally, to find C, we will use the fact that we distributed 2,000 downloads for free, which means that when we first started selling the music at t of 0, we have that p at 0 is 2,000. Evaluating the model we have so far at t equals 0, we get 400,000, our carrying capacity, over 1 plus c e to the negative 0.1 times 0, since we're looking at time 0. We can simplify this using the fact that e to the 0 is just 1, so we can write this as 400,000 over 1 plus c. Now to solve for c, we'll multiply both sides by 1 plus c and divide by 2,000. To get that 1 plus c equals 400,000 divided by 2,000, which is simply 200. This means that c equals 199. So we have now found what L, K, and C all are. So we have found the model that P of t equals 400,000 over 1 plus 199 e to the negative 0.1 t.